I'm Joshua, and this is Jacob, and we are here representing the Clarkson University Nighthawks for the 2021 AIAA Design Build Fly competition. And this year we built a plane called the Magic School Bus because it looks like a bus and it flies. So the overall dimensions of the Magic School Bus is we have a 7-foot fuselage with a cross-sectional area of 9 inches by 9 inches, a wingspan of 5 feet with a chord of 12 inches. For the control surfaces, we have a canard span of 28 inches and a chord of 6 inches. For the tail, we have a span of 30 inches and a chord of 9 inches. And for the vertical stabilizer, we have a span of 15 inches with a chord of 9 inches also.
So to get those dimensions, we started with score analysis based on the rules provided by AIAA to determine how we can maximize our overall score. So when we're doing this, we've determined that mission 2 and mission 3 were inversely related, whereas if we do one good in one, we can't do as well in another one. So on the screen here, we have a life to diameter ratio of 4 on the left and a life to diameter ratio of 8 on the right for the sensor. And for that, we determined that a life to diameter ratio of 8 pushed our sensor life out further for the intersection point between the averages across the design space of those two missions. So with that in mind, we selected a life to diameter ratio of 8 for our sensor in order to push out the design score. So when we were maximizing mission 2, which we determined was going to be easier because it would be easier to make an aircraft that could carry more weight than an aircraft that tow a bigger, heavier sensor. We ended up with a sensor of 20 inches with 2.5 inch diameter and weighs 4 ounces apiece. So that means we can carry 27 sensors during mission 2. So then for our wing platform area, we started with a simple analysis trading off aspect ratio of the wing area to determine what the best platform area was to reduce drag. So we knew a high aspect ratio reduces CDI, which plays a key role in the overall CD as that one increases with a square of CL. From there, we also had the constraints of a 5-inch maximum wingspan of 5 feet and a takeoff distance of 100 feet. So the white space on the plot above is anywhere where that 5-foot span is exceeded, and the line going across about a wing area of 4 feet is where that 100-foot line is not, 100-foot takeoff distance is not met. So our current design space has an aspect ratio of about 5.5 and a wing area of about 5. So next we move down to our propulsion sizes. So for there, this main concern was takeoff distance. So the white space here is anywhere that 100-foot takeoff distance is not met. And shown for mission 2 is our worst takeoff configuration of 25 pounds, which gives us a thrust weight of about 0.8, giving a small margin of error before we reach that 100-foot distance. So in order to get that, we're using a 17x8 prop spun on a power E-Flight Power 60 470 kV motor on a Turnigy 450 milliamp hour battery for a 6S, which gives each motor 10 pounds of thrust. So for the two of them, we get to 20 pounds of thrust required. So then for our control surfaces, for this one, we have twin rudders in our H-tail configuration. For pitch authority, we have canards on the front and a tail elevator in the rear. And then for roll control, we have ailerons that also serve for flaps during high lift. And on the aircraft, we have the ones on the left, right side as yellow, and the ones on the left side as green to help the pilot maintain spatial awareness as he is flying in case the aircraft flips over or when we change directions. So here we have a video of a flight where we didn't take down the nose cone as well as we would have liked. So it flew open, but because we have our control authority that we do, the pilot was able to quickly recover and land smoothly and safely. So then for our predicted performance results, we're predicting a score of 1 for mission 1 because that's just a proof of flight video. For mission 2, we're predicting a score of 1.84, and for mission 3, we're predicting a score of 2.1 for a grand total of 4.94 for an entire flight mission. For takeoff weight, mission 1 is about 13 pounds, mission 2 is about 25, and mission 3 is 15. So for each mission, our cruise speed is between 70 and 80 feet per second, with mission 3 being the tallest. So that is because we have an additional source of drag from the center towing we have to do. And we're Clarkson University Nighthawks, and we will see you out flying.
Here we have a panoramic view of our aircraft, just walking around the outside of it. Note the monocode on the aircraft fuselage was not required when you're flying and is merely for display purposes. Here the pilot is deploying the sensor using his hand to simulate the force of drag in flight when it's being deployed. Here is our lightning sequence, which is just the name of the aircraft, the Magic School Bus, in Morse code. Here the pilot is retracting the sensor using again his hand as a simulation for the drag experienced in flight. Here is our initial takeoff demonstration. The pilot just throttles up and goes straight. So here's a different angle of the same takeoff demonstration. Here is a full flight video demonstrating takeoff and landing with some crews in the middle, similar to Mission 1. Here is our landing demonstration where the pilot comes in for a straight approach. So here the pilot takes off for Mission 3 demonstration with the sensor deployment and retraction. After entering a cruise condition, the pilot begins the deployment cycle where he pitches up and the sensor falls out of the fuselage, and once drag begins acting on it, begins unwinding it from the winch. After the sensor is fully deployed, we enter a steady overflight configuration. The pilot then initiates the retraction mechanism, where the winch goes into reverse direction, pulling it in until the sensor has entered the fuselage.